Hello and welcome everybody. My name is Tristan Shelley. I'm a research engineer here at the University of Southern Queensland as a part of the Centre for Future Materials. Today we will be giving you a high-level overview of the Advanced Composite Pultrusion Manufacturing for Next Generation Civil Structures CRCP project that we have running between USQ, Wagner's CFT, Composite Fibre Technologies, and Allnex Composites. So the CRCP partnership is made up of the lead partner, Wagner's CFT. They're based out at Wellcamp Business Park here in Toowoomba, USQ, and Allnex Composites, who are based in Brisbane. So overall, this program, we're looking to increase productivity of Wagner's pultrusion technologies through novel techniques of preforming, resin technologies, and optimization of Wagner's pultrusion processes, as well as assisting in the development of new technologies to penetrate different markets for Wagner's. Our webinar presenters today will be myself, Dr. Omar Alajama, who is one of my USQ colleagues, Dr. Ali Mohammed, and David Bolin from Wagner's CFT, and we'll also have Dean Boyce speaking from Allnex Composites. So just an overview of CFM for people who are not familiar. We were established in 1995. Last year, we were lucky enough to be named the leading research centre in Australia for engineered fibres composites, which was brilliant, and we were very honoured to get that title. We target delivering research and development which is relevant and applicable to industry. So projects that we're involved in, such as this one, is led by an industry partner, such as Wagner CFT. And we take ideas from our research labs, which can then be applied at our industry partners. The Centre for Future Materials, we have 4 research streams. The one in which the Advanced Composite Pultrusion, CRCP, falls under is our Advanced Composites Manufacturing stream, filament winding and braiding, pultrusion, composite repair, and novel infusion processing and sensoring techniques. We also have a Functional Materials stream, a Civil Composites stream, which this program indirectly links to, and then we also have a Geopolymer and Concrete stream within the centre as well. So getting into more specifics on the project, so pultruded products, and specifically Wagner's pultruded products, can be applied to a number of civil infrastructure applications. For example, pedestrian structures. This is an example of a mangrove facility in Abu Dhabi. One of Wagner's biggest businesses is electrical crossarms, replacing hardwood crossarms for electrical distribution, road bridges, and other civil structures such as jetties. So as I have mentioned before, the primary technology that we're working with is pultrusion, which takes dry fibre in rovings or tows that goes through a wet out process, whether that's resin bath or resin injection. That then leads into a curing die or a heated die, where solid product exits the pultrusion die, is pulled through pullers. There's different varieties and styles of pullers, and then is cut at predetermined lengths. The resin bath is sort of more of an older technology, and this program focuses more on resin injection. USQ as well have a Pultrex pultrusion machine, a commercial size pultrusion machine, in which we can do novel and trial different techniques and methodologies that can't be attempted on a full scale or a machine being used for production. A few different ways of delivering the fibre to the pultrusion dies. There's just basic creel delivery with unidirectional fibres and also off-axis or chop strand mats, which are then wet out and go through the pultrusion process. There's also pull winding, which uses a wound fibre around a mandrel with multiple winders, which can pull through the pultrusion process. And then also more recently, there's been more research done into pull braiding, where the pultrusion machine is also paired with a braider. Just so everyone is aware as well, we are currently or have acquired a dual ring braider for our pultrusion machine at USQ as well. It's a T4L dual ring braider, which we will be using for this program, similar to the top right figure on this slide. Little bit of a busy slide, but it gives a bit of an overview of the pultrusion manufacturing process and how we are taking it and breaking it down into smaller bite-sized pieces for the research which we're conducting as a part of this CRCP. So we have the fibre delivery, which is our work package 3 or fibre architecture, which is looking at analysing and simulating the fibre delivery process and looking at ways of improving the fibre delivery for a reduction or an elimination of defects through to the pultrusion dies, and to look at different techniques for improving the performance of the finished pultruded product. Work package 2, it's looking at the fibre wet out, mainly focused on injection, as that's what our industrial lead uses for production, and using resin bath where necessary for more research activities to feed into production for Wagners CFT. We're also looking at the flow analysis of resin through fibre stacks, which I'll touch on more later. Work package 1 is looking at the heating and curing of the resin through the pultrusion process, through the curing die. Looking at how potentially additives, better functionality of the pultrusion will change the cure kinetics, and also looking to predict how changes in the manufacturing process will affect the final cure percentage or degree of cure of the pultruded product. And then work package 5 and work package 6, focusing more on the structural side of things once we have our pultruded product, but also looking at ways in which it can inform the other processes in terms of improving the performance of the pultruded product. In addition, also having a look at post-processing techniques such as bonding, painting, mechanical fastening, and how we can improve those processes for structures rather than just individual pieces of pultrusion. And then work package 4 is our manufacturing optimization, which runs throughout the process and looks to interlink each of the individual work packages to create overall a much more efficient and productive production line for Wagners CFT. So I will touch on work package 1 through 3. My colleague, Dr. Alajama, will present on work packages 5 and 6. And as mentioned already, overall objective is to increase line speed. So increase in line speed, increase in productivity, increase in profit. So work package 3, working backwards from 3 to 1, is looking at the fiber delivery of the fiber into the pultrusion process. So overall, we want to identify the critical parameters which will help us eliminate defects and improve performance. The simulation you can see here is for a pull winding process. Looking at the image on the right-hand side, the top left simulation is the delivery of the wound layer into the process and the unidirectionals. We then move that fiber stack along the mandrel as if it's been pulled through the pultrusion process. A change in cross-section, there's the defects that can arise as a result of that. And then there's also a compaction process as the fiber stack heads into the injection die and or the curing die. So using these techniques to give us a better idea prior to actually making changes on a production line as to how they're going to affect or influence the quality of the product at the end of the day. So as I alluded to very briefly before, we're looking at how defects generate, whether we can predict those defects, and there's a few different stages within which defects can form. One of those is the deposition of the fiber onto the mandrel when we're pulling through unidirectional fiber or depositing fiber from the winders onto the mandrel. The second is the transition between the circular mandrel into a square hollow or rectangular hollow section if we're not pultruding circular sections. There's also some deformation that can happen at the entry to the injection die, and then as the final sort of stage of compaction into the curing die. I've not alluded to point 4 here, which is some deformation can occur due to the injection of the fiber, or the injection of the resin into the fiber stack. This isn't being looked at in detail in this work package, but will be looked at in detail in work package 2. So there's 2 main mechanisms that cause the defects. These are the shear forces between subsequent layers and also the compaction of the fiber stack at various stages of the pultrusion process. So using finite element analysis to predict these, we need to find some way, without the model being too cumbersome or unable to run within a realistic time frame, we need to find ways of representing individual toes or individual rovings in an FEA model, such as a membrane or a shell element or something similar to that. Apologies if you're not up to speed with FEA terminology, but looking at a way to represent the individual toes on a much higher level or macroscopic level, so that we can have quickly run simulations that can give us an indication as to what changes or how changes will affect the final product. Moving on to work package 2. So this is the infusion work package that we're looking at. So we're looking to model the resin injection pultrusion process, providing tools to improve the wet out rates, which in turn allows us to increase speed, and study novel techniques that may assist us in accelerating the penetration of the resin through the fiber stack. So just a couple of examples here. So blue is no resin and red is infused into the resin stack. So we're looking at over time how the resin will penetrate the fiber stack with different porosities, different resin viscosities, and different line speeds ultimately, which is what we're targeting, to have a look at how we can end up with a quicker manufacturing speed, but still getting full infusion through the fiber stack. So some ways that we've already identified to improve line speed, one of those is simply increasing the die length. That may not be an option for some manufacturers, because increasing the die length means that you need a much or a larger envelope within which to mount your equipment, your dies, and it can also mean that your die is closer to the pullers, and you may not have enough time without means of direct cooling for the product to cool before it gets to the pullers. But all things that can be worked around. Injection pressure. So you can see on the governing equation on the right hand side, an increase in pressure leads to an increase in line speed. But that's not to say that the increase in the pressure of the resin can not affect other parameters, as I mentioned before, such as deviating or causing a defect in the fiber stack. And another option, again, is to reduce the viscosity of the resin. Some future research which is happening is around looking at ultrasonic assisted impregnation, both looking at the ultrasonic treatment of the resin prior to injection, and also the excitation of the injection die for the improvement of resin wet out through the fiber stack, and also looking at novel injection die designs for the accelerated impregnation through the injection die as well. And lastly, resins and additives, work package 1. As a big part of this work package, we're looking to dielectric analysis, or DEA, to investigate the curing performance within the curing die. Because the curing dies are sort of a bit of a black box. We don't really know what's happening. And DEA allows us to measure what's called the log ion viscosity, or ion viscosity. So the sensor sends a current through the resin, and the higher the ion viscosity, the higher the actual physical viscosity of the resin. So you get to a point at which the resin has cured. So what we're looking to do is to fully understand the curing of the dies, of the pultruded products through the dies currently, but then to formulate some new methodologies to improve and accelerate that cure through the pultrusion die. One of those techniques is to increase the temperatures within the curing dies. Currently, a ramp is used with a set temperature at the start and a set temperature at the end. But by increasing the slope of the temperature ramp, which shows an increase in the first heater zone setting, we're able to show that we can kick off the resin, we can start the resin curing earlier within the curing die, which then allows us to be able to increase the line speed of the pultrusion process. And some future activities around work package 1, investigating the effect of the mechanical properties on those increased line speeds, because if you've cured too fast, you may end up with micro cracking within the pultrusion, which may actually lead to a detrimental effect on the mechanical performance of the pultrusion. So investigating all of the effects of the curing process, and also looking at increased functionality of the pultruded product through the addition of additives. The one major one we're looking at is increased fire retardants, which Dean will touch on in more detail later on. We have a large suite of fire testing equipment at USQ, which I won't go into detail with, but we're also looking for other functionalities such as anti-static performance and improve mechanical properties through the addition of some additives as well. So that brings me to the end of my presentation. Do we have any questions from any of the attendees? We have one question that whether the presentation file will be shared. I believe it will be. We'll double check whether there's anything sensitive, but I don't believe there is. So yes, we will likely share the slides, and the presentation itself is being recorded, and that will be sent around to all people who registered at some point in the future. I'm not sure exactly when. Also got a question on the use of phenolic resins in pultrusion. I believe so. I believe it would be possible. We've not used any phenolics at USQ to date on our pultrusion process, but it would the main thing around using or the main drivers around the use of resins is to make sure that the viscosity when it's being injected is low enough to be able to penetrate the fiber stack. There's also considerations around pot life. Generally, that can be gotten around with different resin injection techniques. So if you have a really short pot life material, you can mix at the injection head prior to it entering the injection die. Normally the materials used for a resin bath process have very long pot lives because they're sitting in a bath for a number of hours, or potentially up to a number of hours. But I can't exactly answer a definite yes or no, but I believe there would be ways around using phenolic resins. Fastest speed imaginable. Depends on the product. Depends on the thickness of the product, depends on the shape and size of the product, and depends on what additives are in the product as well. I do know for processes such as there's a flat piece of pultrusion for wind energy, they're hitting speeds of over 2 meters per minute, which is, I feel, is quite fast. I won't say what our industry lead is manufacturing at, but yeah, it is highly application or highly geometrically dependent, and it can also depend on the resin system as well. Round tube, 3 millimeters. You could go pretty quick with that. I would say you're looking at the 2 meters per minute plus. Just due, you don't have a lot of material there, so you'd be able to pull pretty quickly for a 3 millimeter diameter round tube. Cool. Well, I believe I have to pass on to my colleague Omar. So thank you very much, everyone, for listening. If there are any further questions, feel free to put them into the Q&A, and I will type a response. Thank you.
Hi everyone, thanks Tristan for your presentation. I am here, Omar Al-Ajami, and I will talk today on the experimental and modeling tools on the pultrusion composites after let's say on the final product, as Tristan said. So recalling his presentation actually, if we go again to the chart that he explained the work packages, we found out that we can't find that there is two work packages at the end of the pultrusion where we can assist and evaluate the performance of the pultrusion after finishing that process. So in these work packages, we can give the recommendation on if that product is very good to be used actually as structure or infrastructure applications. So starting from the numerical analysis and how that connect to the experimental, and what can we do in terms of experiments in our facilities here at USQ. So the point from having numerical simulation in this project is more about to validate the experiment and go further to optimize the profiles and find out the critical parameters that can affect the structural performance of the pultruded sections. So that we have actually charted that as you see here, let's say starting from the material constituent tests that we can rely on to do actually pultrusion, then doing a small scale testing to find out the laminate properties of the composites. After that, we can do, let's say, large scale testing to simulate the real testing in field. And that input will go to the FEA model to build up the FEA model and try to validate the experimental results. It's not only validating the behavior or the figure, it's also validating the internal stresses inside the pultrusion and find out actually a great matching between the behavior of the FEA and the real testing. So in the next stage, we are heading actually to a parametrical study to study the parameters and assign which one is the critical and how we can actually come up with an optimal, let's say, design for the pultruded composites. If we see that, okay, there is a room for enhancement, we give a recommendation actually for the pultrusion to go and implement that suggestion and go again to the pultrusion and then extract some samples after that to validate our recommendations. So let's say we had softwares, a number of softwares, but we are relying on more Abaqus, let's say, to do some states or steps to build up our models and find out actually the validation of the experiments. The good thing is we are not looking only for validating the results or the experimental results, but we are actually looking for establishing a solid and sound methodology that we can actually validate the experimental results with the easiest way, a quicker way, and that can, let's say, run the models many times. So that we have implemented many ways, and we are end up with a very good actually methodology that can capture the behavior of the composites and capture the instability of the composites, because we are looking and we are talking about thin wall structures that, let's say, suffer from instability behavior. So after that, we plan to go to the parametrical study to select what parameters they are critical to the pultrusion and how can we modify and enhance the performance of the composites after that. We set up, let's say, very critical parameters, starting from geometrical parameters and layout parameters. And we studied actually all of these parameters separately and in combined to see the effect of these parameters on each other. The thing is, we found that some parameters are important and the other parameters are so important actually for composites. And this is actually the main point from doing FEA is to find out actually the optimal design of the composites. And let's say give a confidence in the product, the final product, that there is no no weakness in that product afterwards. And that is affecting the design, that is affecting the material usage, that is affecting the money and the profit after that. Let's say this slide is more about critical manufacturing parameters on compression. And all of us knows that in compression members with a thin wall structure, it suffers from instability, which can cause actually local buckling. And by doing the FEA and validate the experimental results, we were able actually to find the threshold actually that can change or eliminate the local buckling to be compression failure of the cross section. And that can be actually controlled by many parameters, as you see. Going to bending, you can see here that we have validated actually the bending and find out the true behavior of the bending with the current profiles. And from that, it was a starting point actually for us to investigate in deep actually the other parameters that we can actually play around to enhance the structural performance of the composite structures and the bending. And yeah, the good thing actually, we were able actually to enhance both stiffness and the structural or flexural strength as well. So all of these things, we relied on our experiments actually to do those FEA models. And the experiments that we are doing is not only to the FEA, it's more about to test the outcome of the pultrusion with any change in the production line. So for these FEA trials, we assume that the section is going under full cure, and it's basically ideal section. So in the structural lab, we are testing the ideal sections, or the one with a full cure, and with the one with a different, let's say, pultrusion manufacturing parameters, such as line speed and additives and all of these things. So in work practice, let's say, speaking about the hard work and the testing for the composites, and how we can, let's say, identify the structural performance of the composites, and how we can also, let's say, suggest some new testing methodologies that we can standardize that after that. As we know, because there is no actually, let's say, standards or methodology to test the full scale composite structures. Starting from our facility and how, what tests that we can conduct actually in our facilities. Let's say we can do structural tests, small scale, full scale tests. We can do environmental tests as well. We can do fire tests, preliminary, let's say, tests on that. We can also do thermal and physical tests and check for the composites. Looking for the small scale tests, we have the sufficient, let's say, fixtures and jigs to do the standards that are assigned for composites for the small scale testings, and we can do barely, let's say, all the tests that we can actually characterize the composite out of that. The purpose of doing that is to know the laminate properties of the composites, and actually to be a feedback or raw material for the FEA models. After that, to build up our models. Afterwards, we have actually the capacity to do, let's say, full scale testings after, let's say, under compression, bending, shear, and all of these things. So the thing is, those tests are, let's say, being validated from FEA, and by doing these tests, we are, let's say, double check the performance, the structural performance of the pultrusion, let's say, product after that. It's more about also the find out the true behavior of those things to be, let's say, to be used after that in the design, in the design of the structural elements. We have actually sufficient tools and rigs and machines to do those things. We have 3 various size loading frames, up to 2000 kilonewton. We can implement, let's say, columns, beams under those machines. We have also fatigue rig with a 500 kilonewton capacity. So after testing those things, we are not looking only for the behavior of load displacement behavior, for example, or those things, but we are, let's say, dig in deep inside to analyze the failure and the failure progression of those composites. The reason for that is more about, let's say, identifying the weakness points that we can actually do a recommendation for the pultrusion after that. Okay, this is a weak point, you can implement, let's say, or modify that or strengthen that by doing those, for example, steps. And we are using actually many microscopes that we have, and we are using also SEM that we can actually see the bonding and the interface between the fibers and resin, and what is the interface between them. All of these tests we can do actually those tests without a special touch from USQ. As we know, there is no standard for testing the full scale structure in composites, but we were able actually to introduce and design new testing rigs that we can rely on actually to get the true behavior of the composites, starting from end fixtures and loading points for the bending. And actually we were able to get a true behavior out of those composites and get rid of any failure concentration, let's say failures out of stresses concentration at the ends and the interface between the loading point and the cross section as well. Beside that, we have also let's say successful in suggesting new methodologies to characterize the curved sections, which is no one have done that before. We were able actually to do coupon testing in compression and tension using a special design for end fixtures. We also have done a transverse compression methodology for the rings or the pipelines, because to get rid of the ovalization that is happening, let's say, when you apply a load to the ring or the pipeline. And that gave us actually a very confident and sound results afterwards. I need to highlight something here. More important is we have special tools such as DIC, not only to find the results of or let's say to capture the results during let's say during the test, but also to validate and give us a confidence in what we are doing actually at USQ here. We also, let's say, double check the FEA models that we have using the DIC, and let's say even double check the theories that built up before on the composites. And it helped a lot before actually in identifying the local bucklings and identifying the failure features of the composites. After, let's say, after the pultrusion, there is many post-processing steps that the manufacturer using, especially, let's say, drilling holes, inserting some insert inside, doing bonding and painting. And we were able actually to benefit from the square sections into introduce, let's say, new cross sections like the figure that you see in the left hand side at the top. We were able actually to introduce new I sections, C sections, and L sections out of end product, Square end product, and actually the results are quite sound on that. So we can also benefit the manufacturer to increase the product sections and increase the design guidelines actually on that. So we were able actually to test the composites with holes and inserts and find out what is the effect of those post-processings on the cross sections, because those defects, let's say, can in some stages can affect the structural performance. We were able actually to test some adhesives to find out the best bonding or gluing for the composites to get the true or the, let's say, the limit of bonding capacity. Also, we have, let's say, testing and also managing to test some fasteners capacities in composites. Aside of structural testing, we have done some preliminary testing, fire testing on composites. So we have two main rigs actually on the, let's say, to test the smoke density of the composites, toxicity, and also to characterize the ignition properties, let's say starting from the start point of the ignition and the duration of the ignition. And you can see here some of the test results on the composites that we have done. Also, that can be extended to test the fire performance of the composites with fire retardant and with the special painting and coating of the composites. We also have done, and we are managing to do as well, environmental testing of the composites, and that is relating to accelerating agents applied to the composites to find out the life and prediction of the composites. We can apply many conditions on the composites, starting from the UV radiation, going to the hygrothermal effect, including moisture and temperature, and we are going also for elevated temperature of the composites. We are, let's say, that the aim of that is to initiate some master curves on the real testing time and extend that actually to see what is the life prediction of the composites in years after that. All of these things and facilities are happening at USQ. We are also managing to do many tests as much as possible in the future, and we have the ability actually to expand our research in further. So this is the end of my presentation, and I'm happy actually to answer any question from you guys. Thank you so much. So we have one question from Tafsi on, in the FEA model, did you model the FRP tube as a composite laminate material or layer by layer? How you apply the winding angle in the FEA model? This is a good question. Thanks for that, Tafsir. We have tried that many times, and we end up with a. Actually, we did both of methodologies, and let's say summarize the answer by, we have adopted the first methodology. Why? Because it saves a lot of time. This is first thing. The second thing, Abaqus can give you actually the initiation of the failure between the layers, and that was actually the point we rely on to, or let's say a justification to have approach the first one. For the applied winding angle, Abacus can give you a composite laminate option, so you can even do a solid wall, but with different layers, and you can specify the angle of the fibers based on how many numbers of layers you are input. Any question? Yeah, good question from Pink. Actually, he is asking about if FEA model can simulate the pre-failure or post-failure cracking on the pultruded profile. Yes, it is actually by using the failure category, let's say in Abacus, or let's say on the software, it can give you actually the stresses, how the failure is initiated, and what's the end of the failure based on the material properties that you can input, and possibly validated by the DIC results. So the DIC is a 2D, actually, that the one that we have is a 2D machine instrument that can give you the outer surface actually strain change. But in that strain change, you can see the stresses concentrations and where is the initiation of the failure, and how can be extended after that based on the outer surface, not the through thickness. So we are relying on the FEA to go in deep through thickness, and the DIC can validate the outer surface. We have another question on for the transverse compression test of circular sections. Is that based on standard? What loading condition you are simulating, as most transverse loading are occurring locally and not uniformly? This is a good question, and this is why we have initiated that type of test. It's not standardized, and there is no standard actually looking for that. And we, because of there is a non-uniformity in the stresses through the cross section, we designed the new fixture and testing rig actually to get the true transverse compression of the pipelines. So I think I run out of the time, so I will handle the floor to the industrial partner to speak about utility poles and the manufacturing and the performance of utility poles. Thanks for that. Ali, you can start, please.
Hi, Omar. Thank you. Thank you for the introduction. Let me share my screen. Just freeze. All right. Hello, everyone. Can anyone confirm that you can see my screen and you can hear me well?
Yes, Ali.
Yep. Thank you, Omar. Good afternoon, everyone. I am Ali Mohammed. I am product engineer at Wagner CFT, and today I'm going to talk about the FRB composite utility balls. At the start, I would like to give an outline about my presentation today. So first, I will give a brief introduction about Wagner CFT and about the FRB structural sections that has been manufactured here, and the pultrusion properties of the sections that have been manufactured, and how these different sections are being used as a product or they are being used as full structures. As been asked, I've been received this request from the host. Let me start my video. Yep. So going back to the outlines. Yeah. So I will present the properties of the sections that we manufacture here and how these sections are being used as individual products, or how they can be assembled together and being used as a full structures. And then I will talk about like why we are jumping into this new venue of manufacturing FRB utility balls. And I will explain the design requirement and the design process, the structural testing that has been done, and then the analysis, the numerical and structural analysis that has been done in this testing. And then I will conclude my presentation. So Wagner CFT, like the head office of Wagner CFT and Wagner's overall is in Toowoomba, Queensland. And as you can see in this photo, this is the Wagner CFT office and the factory, where more than 150 full-time employees are working on on 4 pultrusion lines and manufacturing nearly like 500 Ks of pultrusion per year, and that's making Wagner CFT as the biggest pultruder in the Southern Hemisphere. So a sneak peek about the factory. As you can see here, these are our 4 pultrusion lines. Like the first pultrusion line started back in 2002 and manufacturing all various sections. And as you can see on the back, that is the glass room where all the glass is being kept, and also where the unique pull winding process of Wagner CFT is being located. With this unique pull winding process, it's giving us like the high fiber content, which will result in better mechanical properties, as I will explain that more in details in the coming slides. Next, this is kind of like a summary of what we are currently manufacturing in terms of structural hollow sections. So we manufacture circular hollow sections, square hollow sections, and rectangular hollow sections, and each section of that can be produced with different sectional geometry and properties, and with different wall thicknesses to cover a wide range of applications. As I mentioned earlier about the ball winding process. So the ball winding process will result in better physical properties, and as we can see in this slide, which present the physical properties of Wagner's pultrusion. And the main thing that to look at here in this slide is the fiber mass fraction and fiber volume fraction, which is nearly 80% and 60% respectively, which is one of the highest fiber content of the current pultrusion in the world. So with this high fiber content, and plus the quality of the fibers and the resin mixes that is being used, definitely that would result in very high mechanical properties, as we can see in the next slide, with the mechanical properties of Wagner's pultrusion with a tensile strength of over 600 MPa and a modulus of over than 35 GPa, And these are the characteristic values as per ASTM 7290. So with all these high mechanical properties, this enabled us like to use these products in various structural products as individual products and as in full structures. So as we can see here, these are a few examples of Wagner's pultrusion is being used as different product in different applications. So as we can see in the first photo on the top left corner, where Wagner's FRB section is being used as a cross arm, and in the second photo it's being used as a light pole, and also it's being used as a columns for a shelter or light structures, and also it can be used as a ground pile, as a foundation. So all these product require like minor finishing, minor modification on the surface to suit that specific application. For example, for the cross arms, we need a special surface treatment or surface treatment to give it like the proper electrical properties, and this kind of surface treatment is not required for the pile, and it's the same for every single application. In addition, these individual sections can be assembled together, as we can see in this photo, where several structural sections has been bonded together, forming bigger sections and achieving higher strength and higher stiffness. And following this bonding technique that I believe David will talk more in detail about it. And with this bonding technique, we can produce and we can establish or fabricate, let's say, larger structures, as we can see in the next slide, where a few examples where FRB of Wagner's FRB sections has been used, like in road bridges, staircases, and many other applications, structural applications, like over 1,000 of boardwalks and pontoons, so many other marine applications. So the next venue that we need to conquer is the FRB utility pole. So why the next section need to be used as FRB utility pole? Due to the huge demand in the market about the FRB utility poles or the FRB poles in general, we decided to jump in like with bigger sections to meet the structural requirement of the utility poles. And why it's FRB, as you all aware, because of the superior properties of the FRB composite material compared to traditional materials such as timber and steel, and also the environmental performance of the FRB composite material in general, where the less carbon emission is being produced due to the process, due to like the overall process of FRB, like fabrication and utilization, as shown by many studies about the life cycle assessment of FRB composite material. So for the design requirement of FRB utility poles, there are various requirements to be met to fabricate or manufacture or produce an FRB utility pole. The first one is the fire resistance. So the fire resistance of FRB utility pole, it need to meet like the BAL 40 requirement, as you can see in this photo. Like it's the next phase of push fire, which is the first phase is the fire zone, and the next one is BAL 40, which is very harsh condition like to resist. The second one is the durability. The FRB utility pole need to have like certain weathering performance, so it can meet like the longevity and achieve the design life for the specified utility FRB poles. And the third one is the electrical performance. The FRB composite material have good electrical performance in terms of basic impulse level and base, and also like arcing and tracking. So there's also many other requirements for the electrical performance that need to be met. But with the composite material and with the surface treatment that we use for the composite cross arm, so there will be no issue in the electrical performance. And the final one, which is I'm going to talk mainly about, is the structural performance of the future FRB utility poles. So the FRB utility poles need to meet the serviceability limit state and the ultimate limit state as per ANZS 7000/2016, which is the Australian standard that has been used for the FRB utility poles. So basically, what is being done here, we have done structural testing according to AS 7000 on the current profiles that we have to establish the flexural strength and the full section flexural modulus on the current profile, and extrapolate the values that we got on the design of the future profile to meet the same structural requirement. So below in this figure, we can see the test setup, which is basically like two supports at the bottom, which is A and B, which is at the left side of the picture. So we have the bottom support, and we have the second support, which represent the ground line mark, where the stress concentration will be, and two roller support, 2 or 3 roller supports depends on the length of the utility pole and the loading point. So in the next slide, the full scale testing is shown following the AS 7000, and this sample is being loaded till failure. And as you can see in the graph that's shown in this slide as well, so you can see the sample is behaved linearly till failure, which is expected from FRB composites. But if we want to look further and look more in detail in this slide, so basically the serviceability limit state for the utility pole, it's 5% deflection of the above ground height. So basically for this utility pole, because due to it is a smaller section which is not being designed as a utility pole, so the design capacity would be 2 kilonewton, because that's where we get like our 5% deflection, which is around 500 millimeter, and the ultimate limit state is 3 times the working load or serviceable limit state. So that means that if we want to use this section as a utility pole, it needs to be designed for 2 kilonewton as a serviceable load and 6 kilonewton as ultimate for the ultimate limit state. So the 6 kilonewton capacity is almost half of the actual capacity of the FRB utility pole, and this is the issue with all FRB composites. They are like in the design they are designed for a fraction of its actual strength, because it's usually governed by the deflection. So following this full scale testing, structural analysis. Before going to the structural analysis, sorry, we need to talk about the failure mode, how the sample is failed. The sample failed at the ground line, at compression failure, in a moment of like 110 kilonewton a meter, which is what we were expecting. Following this full scale testing, structural analysis has been done using space gas software, and also the spreadsheet has been developed to ascertain like the sectional properties that we need to achieve the design requirement for a future utility pole, which we need to meet is 4 kilonewton and 6 kilonewton utility tip load at the top of the utility pole. So as we can see in the bottom spreadsheet, the snip of the spreadsheet, the future profile will end up like with 293 millimeter outer diameter with a wall thickness 9.5, and the second one will be 301 millimeter and 13.5 millimeter wall thickness. This will be sufficient to meet the structural design requirement for the utility pole with a working load of 4 and 6 kilonewton, and also which means the ultimate limit, the ultimate load will be like 12 and 18 kilonewton. And further FEA analysis has been done where the experimental result has been verified, and looking at the layup and the wind angle of the of the future FRB utility pole. So as we can see in the graph on the left side, where the experimental are matching matching the first model that has been done on the current wind angle with 50 degree. Then with the validated model, the wind angle has been changed and reduced by 20 degree, and that resulted in an increase in the flexural stiffness and the flexural strength by around 7 to 8%. This model has been done by one of the BRT students at USQ that has been funded through this CRCP project, and I would like to thank him for this model. So after this full analysis, like, we are confident with our future utility poles, and we are going to start manufacturing in the first half of this year. So here I conclude my presentation for today, and at the conclusion, I would like to say that I have presented like a various of FRB products made of our FRB sections, and what I've presented are only a few examples of what's actually been used. And in this photo, you can see our FRB composite product used by another company, Composite Stand, that we worked with them together to develop this product, and it's being used as a jack stand for heavy machinery, replacing the steel jack stands. And the weight of this composite stand, like, is a fraction of the tremendous and heavy steel jack stand. So what I'm trying to say here, like, if you have an application and you believe the FRB composite would be the solution, feel free to contact us on my email, and we can work on develop the future product together. Thank you for your listening, and let us see if there is any questions.
Thanks, Ali, for your presentation and the informative, actually, information that you have presented. Actually, the audience and the attendees are welcome to ask any question for Ali. You have one question here, Ali.
Yep, I cannot see any question in the chat. So
you can go to the Q&A section. Q&A. At the bottom, next to the chat bottom. Yeah.
My question is related to the FEA analysis of the electric pole. It looks like the analysis is linear, but I believe that does a slender member, the tendency to buckle is high as shown as from your experiment. That's a good question from the anonymous attendee. So the question is basically asking that about the buckling, about the buckling of the FRB utility pole. So basically what happened in the future, basically what happened on the finite element analysis, the finite element analysis that has been done is just to capture the moment of failure, and the FEA analysis is not being continued about the post-processing, about the post-failure method. So basically, if there will be any buckling or the buckling would be captured by the post failure, but the FEA is being stopped at the moment of failure, where the hashing, following hashing damage model, and it's been where the value is equal to 1, that means there is a failure, and the failure, as we can see in that, as shown in the slide, it was in the compression of the matrix. Hopefully that's answer your question, and if you want to discuss that further, like feel free to shoot me an email. Thank you. Okay, if there are no more questions, I will hand over to my colleague.
I think, Ali, it might be some actually people that are writing. If we can we, let's say, have another minute just to wait?
Sure. Yep, yeah, sure.
Thanks for that. Ali, thanks for presentation. I have actually a comment here. So you are introducing, as a manufacturer, you are introducing, let's say, new sections to fulfill the design limitation of the electrical poles and utility poles, isn't it?
Yep.
Yep. You have another question, I think, here.
Yeah, basically the durability requirement in the design is being factored. Sorry, like the question is about how do you account durability requirements in your design of composite structures using your products. So basically the durability, there are several factors that need to be considered at the design stage, considering the environmental parameters such as durability, such as the humidity, temperature, and the creep. And there are certain factors that need to be applied for the long-term loading and for the short-term loading based on the code that you're following, whether it's the Eurocomp or the BREEAM standard or it's the JRC. So basically, it's been factored, and as shown in the full-scale testing that has been done, the ultimate failure load is almost double the ultimate limit state requirement. So it's even applying these factors, like the ultimate limit state and the durability limit state, it still can be factored.
Thanks for that, Ali. Guys, any question, let's say, can be sent to Ali, directly to Ali to have the answer for that. Thank you so much, Ali. And let's go to David Pullen, actually, to talk about bonding techniques and technology implemented actually in Wagner so far. Thanks, Ali. Welcome, David.
Yeah, good afternoon, everyone. Hope everyone's enjoying the presentation so far. My name's David, and I'm an engineer at Wagner's alongside Ali and a few others. I'll just open up my presentation and get underway. Omar, can you just confirm you can see my screen and can hear me properly?
Yep, David, all good.
Perfect, thank you. So my topic today is talking about obviously our pull-threaded composites and some of the various methods that we have looked at and even use on site to treat the surface of those composites for a variety of processes that we do here on site. So in the context of this presentation, I'll be talking about adhesive bonding and surface treatment. But there's also a variety of other things that we do on site, such as painting and a few other bits and pieces that involve service prep. Just keep in mind that this presentation is in the context of an adhesive bond. So just a bit of an overview of what I'll be talking about. So I'll just go through the basics of what I mean by an adhesive bond, and then try and talk about, what is surface treatment, why is it important, what does it actually mean, how do you do it, and how do you actually evaluate whether a surface has been properly treated for bonding. And along the way, I'll provide a few bits and pieces from what we do in-house, and a few comparisons between various things that we've tried, just to demonstrate how various things work. So just very quickly about me, I'm a mechanical engineer. I've been here almost 3 years, and I work in the R&D department, doing a whole different array of things, but particularly on this subject, a lot to do with bonding, a lot to do with polymers, adhesives, and coatings, and all very relevant to Wagner's Composites as a whole, where we do bridges and boardwalks, and we paint things and we bond things together. So adhesive bonding, what do I mean by that? I mean the process whereby you are joining materials together with an adhesive. The materials can be of the same type, or they can be similar types, but it finds an application in almost all industries. Aerospace, wind generation, power generation, medical, almost everywhere you've got applications of adhesive bonding and bonding materials together to form a structural bond, so to speak. A whole bunch of different terminology that's used in this field, adhesives, substrates, bond lines, etc., etc. I'll try and keep it as basic as I can for those of you listening who are not too familiar with this field. But just on the right there, just for interest, that they've even developed an epoxy or not an epoxy, an adhesive for repairing bones up in the space station. So they call it tetranite, and it can be used to glue bones together. So even our astronauts are using adhesives for medical purposes. So such a very broad range of industries, and can be quite amazing to see it being used for a variety of different things. So the bond itself, the adhesive bond itself, is formed of typically the substrates, which are the materials that you want to bond together, and then the adhesive. And obviously, it forms a sandwich of the two substrates and the adhesive in between. In the area directly where the adhesive touches either substrate is called the bond interface. So the role of the adhesive is to essentially form a structural bridge between the two substrates, and that takes the loading conditions and also transfers the stress from those loading conditions between the two substrates. So effectively, you want to join two substrates together to form a cohesive material via this adhesive. The main critical requirements for an adhesive bond are obviously the adhesive properties themselves have to be strong and tough, and the right elongation to suit the expected stresses and loads. And then the details of the actual interfacial bond between the adhesive and the substrate. You want either a chemical bond, a mechanical bond, or ideally both. And then the actual wet out of those substrates via the adhesive is another function, and also governs the interfacial strength. So today we're looking very in depth at the wet out, or how the adhesive coats each substrate to give a very high surface area for the bond, so to speak. And obviously, there are other aspects to the bond as well, such as mixing your adhesive properly, curing it properly, etc., etc. Just on the right there at the bottom is how we use adhesive bonding on site. One of the ways, that's one of our bridges, and we bond some of our sections together in a laminating type setup. So at the bottom of that bridge, you can see three of our composite sections bonded together to form a 3-stack high. So if we zoom in on that subject of wetting of the substrates with the adhesive. Obviously, the objective is to get good wetting. So the adhesive thoroughly coats each substrate and gives really good contact between the two. Good wetting is your high contact area with the substrate. Bad wetting is low contact area. You can see on the right just a bit of a visual of an adhesive that's wet, a substrate, quite a rough substrate, but on the top's the good wetting. You can see it. The adhesive's flowed into all the little nooks and crannies and has formed quite a high surface area with the substrate versus the bottom where the adhesive is forming gaps and hasn't flowed across the surface. So if we're looking for good wet out, and it's a critical component to achieving a good bond, how do we achieve good wet out? Well, let's look at what governs wet out, and that is a term called surface energy. All surfaces have what's called surface energy, and it's essentially the attraction force on the surface of that material. So the atoms, high surface energy materials, the atoms are very strongly attracted to each other, and that results in a very high attractive force on the surface of that material. And the opposite is obviously a low surface energy material where the atoms are not so strongly attracted to each other, and you get a low attractive force on the surface, or a low surface energy. Both the substrate and the adhesive have a surface energy, and it is measurable. And just to summarize, to get good wet out where you want the adhesive flowing across the surface well, you want a substrate with high surface energy. And ideally, it's a higher surface energy than the adhesive. High surface energy is a high attractive force. The adhesive is going to wet out the surface. When we look at CFT and composites in general, there are a few difficulties with looking for high surface energy for good wet out. The main one is that glass fiber composite has an inherent low surface energy, so it's difficult for an adhesive to wet the surface out. So just from the get-go, we need to look at options to increase our surface energy for better wetting out of the adhesive. We also use other materials here on site that are all very low surface energy materials, so polyester plastics, polyolefin plastics, and also fluoropolymer type materials. These are all low surface energy materials. So in general, we have a difficult time bonding here on site. The other aspect of a good bond, aside from the surface energy of the surface, is the presence of any contaminants on the surface before you bond. So contaminants can take the form of dust or fingerprints. A big one is obviously silicon contamination. Silicon is quite often banned in a lot of industries, aerospace, et cetera, where they do critical and large scale bonding because it is such a bad industrial contaminant. You know, even a tiny amount of silicon on the surface can affect your bond quite significantly. On the right there, you can see, well, very, very bad silicon contamination on the surface has been painted, and you can see it beading up, showing how the paint is not wetting out that surface and coating it because of that contamination. If we dive down into what contaminants actually do, because they exist on the surface of a material, their surface energy affects the surface energy of the substrate. So whatever the contaminant is, then that affects the surface energy of the substrate because it exists on the surface. And aside from that, the contaminants exist as a layer between the substrate and the adhesive. So even if you bond up a substrate with a contaminant and get a very good bond to the contaminant layer, the bond between the contaminant and the substrate could still be weak, and you get a poor bond no matter what you do. So ideally, before you do a bonding operation, you remove all contaminants and ensure that everything is very, very clean to eliminate the risk of this sort of stuff happening. But the good news is that surface energy, or measuring surface energy, can be used to detect these contaminants. If you have a surface that you know it's surface energy, you've measured it, then you test again and find it to be different, you can more often than not assume that there is some sort of contaminant or there's something different about that surface. And you can look into why that is and what to do about it. So just to summarize the last couple of slides, what do we need for good wet out of our adhesive onto these substrates? We want high surface energy of our substrate so that adhesive flows across. we want a clean substrate, so no contaminants on the surface. Now, if we achieve both of these things, we should be getting closer towards a good bond. Obviously, there's a few other factors there as well. But how do we actually assess whether we've achieved a higher service energy in a clean substrate? How do we assess that and evaluate, our surface that we're about to bond to? Before I answer that, I just got a bit of a real life example here, which I found back when the F111s were in operation in Australia. They were finding the sandwich panels were delaminating and debonding. They found that a large number of them were from repairs where there was no surface preparation. So it just highlights how important surface preparation is to eliminate or to reduce your defects and to improve the consistency of your bonds. Okay, so we've asked ourselves how do we actually measure or evaluate the surface energy of a surface? The most common way to do it these days, back in the day, or let me start, back in the day they used dine pens and various other things like that, whereby you were given a set of pens that you used to mark a surface, and that pen would then indicate whether the surface was high or low surface energy and give you a rough approximation of what that surface energy was. But these days we've gotten a lot more advanced. So the best way to do it is if you've got a consistent way of measuring. So your substrate's the variable. You want to know what your surface energy of your substrate is. So the way you measure it should be consistent. So you start off with a liquid, most often some sort of very clean water, and they use a water drop and how it interacts with the surface to assess the surface energy of that substrate. So on the right, you can see a water drop on a substrate and how it interacts under various wetting situations. So on the top, you've got bad wetting, whereby the water drop does not flow on the surface and doesn't wet it out. It actually sits almost as a drop entirely on the surface. In the middle, you've got what we call good wetting, where the drops flowed out and wet the surface, and the bottom is obviously very, very good wetting. Now, to actually standardize this, they measure the angle between the water drop wall and the surface. So that angle between that water drop wall and the surface is given the name contact angle. And a high contact angle, which you can see in the top one, is a representation of bad wetting, whereby the drop hasn't flowed, and a low contact angle indicates very good wetting or very high surface energy, where the drop has flowed across the surface. So if you can somehow apply a drop of water to the surface and look at how the drop interacts, you can measure and get a very consistent way of measuring how that surface, how the surface energy of that surface is at. Now, they've made machines that do this. A variety of different suppliers make machines that fire a drop of water at the surface and then can tell you exactly what the contact angle of that water droplet to that surface is. And you can then use that to consistently determine the surface energy of your surface. So it fires a known volume of water at the surface, and then photographs the drop sitting on the surface. And then either from a side profile or top view, it calculates the contact angle of that water drop. On the right, you can see one of the many pieces of software that can do this process. Here at Wagners, we've got a very portable piece of equipment that does this process for us. We can use it to check the contact angle of almost any surface, whether it's horizontal or vertical or upside down. And these are available from quite a few manufacturers around the world. Here's a bit of a real world example where we've used this contact angle device to check for silicon contamination. We've purposely rubbed a piece of pultrusion with silicon, and we've measured the contact angle of that surface before and after that silicon's been rubbed on the surface. And you can see the bottom half is just the untreated pultrusion, so it hasn't been rubbed with silicon, sitting around the high 40s, 50-degree contact angle. And the top half is the surface after it's been rubbed with silicon. So you can see how this device and this unit of contact angle can be used to assess a surface and assess the contamination on the surface, or assess the surface energy of a surface, so to speak. We found it to be very handy, and it's still teaching us things every day in terms of our bonding process and things we do here at Wagners. So if we go back to our list of what can we do to increase or to better prepare our surface, one is obviously increasing the surface energy, making the surface easier for the adhesive to wet out. There are many options available these days for increasing the surface energy of difficult to wet substrates. Here are a few here, which quite a few of you probably heard of. There's flame treatment, corona treatment, plasma treatment, and then there's mechanical type treatments. And I'll just go through these quickly. We've actually tried all of these here at Wagners, and I've seen good results with some and not so good with others. It obviously is very dependent on what your application is and what you're using your substrates for. So the first one, and probably one of the most common, is a flame treatment type unit. It's a gas flame. It's commonly butane or propane or some sort of flammable gas in the shape of a very high energy jet. It's typically got two cones to it, the jet, and the inner cone, the darker or the deeper, more vivid blue cone, is the reactive type or reactive part of that flame. And when that flame is run over the substrate, that flame gives the substrate a higher surface energy because that flame is chemically active, so to speak. It changes the substrate surface and gives it higher surface energy and a better bonding surface. One thing to note is that depending on what you're bonding to, the fuel type can change. We found more success with a butane type burner. So I've got a bit of a comparison here between a control set propane and a butane type flame treatment on our pultrusion. You can see the control surface hovers about 50 degrees contact angle. We apply propane flame to the surface. You can get it down to about 24 if you change the way that flame is applied. We use a blade type burner and a pin type burner. However, if you use butane, you get that surface contact angle down to a very low number. So for our pultrusion, we found that most commonly butane gas to be the best if we're going to flame treat our surface. The next one is corona treatment. It's whereby high voltage, high frequency current is passed through an electrode, and that generates a corona type field. On the right, you can see what it looks like. So it's a blue field, and you can use this to run over your low surface energy substrates and to increase their surface energy. It's also known as blown arc industry term. It's quite good for high line speeds. So if you've got a continuous sort of plastic processing operation or some operation that requires high throughput, it's quite good for that. It's very, very common for treating your polyolefin type plastics or your polypropylene, et cetera, and then the third one, and probably the one that's considered the best, so to speak, is plasma or blown ion, it's called. It's a very energetic, very high voltage type of surface treatment. It can achieve very, very high line speeds because it is so energetic. It doesn't need much time to increase the surface energy of a substrate. However, it can overtreat if you're not careful, you haven't calibrated your line properly, you can overtreat a surface. You can see detrimental adhesion from overtreating with plasma. And as I said, it's typically seen as the most powerful or effective option for low surface energy substrates. We had our pultrusion treated with corona, plasma, and with flame by a third-party company. And here's just a brief overview of those results. In the center, you can see the contact angle measured with the three different types. And as a general comment, we saw good results, a good reduction in that contact angle, meaning that the surface was a high surface energy with all three types. Obviously, it'll depend on your composite, on your resin, on your chemistry, all that sort of stuff. But you can typically calibrate the line speed, the gap between the corona or plasma applicator head or the flame, and the power output to achieve, a pretty good result from the raw surface. So that was our experience, and that all three gave reduction in contact angle. But typically at the moment we've preferred to use flame for our processes. The other one, which is a bit different, but can also be used to modify a surface or treat a surface, is mechanical type treatments. That's abrasion or sanding or grip blasting, something that etches the surface or gives the surface a different texture or a different feel. There's a few different things, not just increasing the surface energy. Because it's removing a layer of the surface, it can remove contamination. So it's a double win, really. Second thing is that it roughens the surface, as I talked about. And the third thing is that it actually refreshes the surface chemistry. If you're dealing with a thermoset type material like our pultrusion, sometimes the surface is quite inert because the resin itself is almost fully cured. So it's just general, it's very hard to bond to aside from the surface energy. So if you abrade it, you can sometimes dig down and find a more reactive surface in terms of the chemistry in there. So mechanical, definitely don't rule it out if you're looking at something like that. It can do quite a few things, and it can definitely bring benefit to a bonding process. One thing I will note is that if you're using an abrasive type process, just watch for contamination. If that abrasive itself is actually contaminating the surface, or whether, for example, this brush on the right, it's a nylon type brush. If that's smearing on the surface, getting hot, it can leave a contaminant on the surface. So you always have to be very careful with these sort of physical contact type applications, that you're not worsening it by leaving something behind on the surface. Here's another example of what we've done something in-house, whereby we looked at abrasion versus flame treating. On the bottom is the abrasion, so you can see that for us, abrasion doesn't give a massive benefit in terms of better wetting or higher surface energy, but for us it helps with cleaning the surface and removing contaminants. And obviously the top is the flame treat, so we get a very good result from flame treatment and see very, very, very low contact angles. So yeah, we get great benefit from flame treating for our bonding processes. One other thing I'll mention in terms of contaminants. So we looked at how to increase the surface energy of surfaces, but the other thing is how to deal with contaminants on the surface. So most common way, I'll just touch on it briefly, is via cleaning with a solvent. So acetone, ethanol, MEKP, all that sort of stuff is commonly used in industry. You can also buy specific cloths and wipes on the right. There you can see specific wipes designed to remove contaminants, to aid bonding. There's heaps of stuff out there you can research and trial and test that'll help with the removal of contaminants. Just a few notes is that when you're doing this cleaning process, that everything has to be clean. So if you have a contaminated substrate and you wipe it with a clean cloth, you should never re-wipe that surface with that same cloth. You should always be using something clean on that surface every time. Otherwise, you'll be just redistributing that contaminant back onto the surface as you wipe over and over, so to speak. So you want to use fresh solvent, fresh cloth, and the right wiping methods. And there's either develop your own wiping method, or there's a bunch of standards out there that you can use to see what the industry uses in terms of the wiping method. You know, do you wipe in one direction all the time? Do you wipe in two directions, etc., etc.? So there's definitely standards out there you can visit or look into it yourself. For ourselves, we found that wiping, as I've explained, doesn't actually help with our surface energy that much. Yeah, but here you can see that by acetone wiping our pultrusion, you get a reduction in contact angle. So you could suppose in this test that there was some sort of contaminant on the surface. You go down from 70 degrees or so contact angle to 50 degrees after you acetone wipe. So that's the sort of difference you'd be looking for if you suspected a surface was contaminated. You'd be able to see via measuring that contact angle that the surface is improved after you wipe it. So just to summarize, good wet out of the adhesive between two substrates for a bond is critical. And And the wet out is a function of both the surface energies of the substrates and the presence of any contaminants. You can use the surface energy to evaluate how your service is going in terms of ready for bonding. There are machines available that can measure this, and you can use a variety of different techniques and processes to increase your surface energy of your substrates for that bond. And then obviously contaminants are a no-no, and you should be looking at ways to reduce exposure to those contaminants. So as I said, some people have banned silicon in industries and that sort of thing, so quite serious. But you should be looking at whether you can remove or take away any sort of contamination process from your bonding area in your factory, if that's your setup. So anyone got any questions?
Thanks, David, for your presentation, and the attendees are welcome actually to ask any question they want. So if there is no question, let me thank you, David, for your presentation, and I will type your contact details for any question, let's say, which can be, let's say, sent through email.
Yep.
Thanks for that. Now, can I invite Dean from Allnex to speak about the technologies and the techniques happen in Allnex, and provide us with the latest, let's say, development.
Sure, thanks, Omar.
Thanks,
I'll
Dean.
share my screen. Just let me know. Let me know. Can you see there, Omar?
Yeah, I see that now. Yep, exactly.
Okay, that's all good.
Yep.
Okay.
Thanks.
All right, good afternoon, everybody. My name is Dean Voice. I'm the Technical Manager for the Composites Division of Allnex Resins here in Australia. And today I'll talk a little bit about some of the work that we have in progress as part of this program, this R&D collaboration, to develop a new fire retardant VE pultrusion resin, or fire retardant resin options for Wagners in this project. So I'll just give a bit of background on Allnex. I'll keep this as brief as I can, and then I'll go into some general information on different fire retardants leading into the actual, some of the work that we've been doing, a slice of the work that's showing some promise now in development of a suitable fire retardant vinyl ester. So background on the Allnex business. Allnex is a global leader in the market for surface coatings raw materials, in fact, which forms the core of the business worldwide. The business has expanded over the years with various acquisitions and mergers with other major chemical companies, and is now one of the largest global producers of coatings, resins and other raw materials for surface coatings. But Allnex also produces unsaturated polyester and vinyl ester-based products for the composites industry, and is a major producer and supplier of these products in Australasia in particular here, where we were formerly Nuplex. In 2016, there was an expansion of the Allnex Composites business following the acquisition and merger with Nuplex here in this part of the world. So globally, apart from having a strong coatings resins business, Nuplex was also an established leader in the Australasian composites resins market, producing unsaturated polyesters, vinyl esters and gel coats. Just a little on our global footprint. We have, Allnex operates 32 manufacturing sites with 23 R&D centres, at last count I believe, as I understand it, and there are 5 joint ventures involved globally. We've got various composite resin manufacturing sites locations including Australia, Indonesia, Vietnam, and Europe. There's also a large plant in Germany, in Bitterfeld, which produces some specialty unsaturated polyesters for putty and knifing putty applications, among other things, a Roskadal range of products there. The main Allnex site for the manufacture of unsaturated polyester resins, gel coats and vinyl ester resins here is located here in Australia at our Wacol plant in Brisbane. And our R&D centre for composites materials, mostly involved in resin chemistry and development of new resins and gel coats, is located at our Botany Sydney site, our plant facility down there. But we've also got another lab here in Wacol. I won't dwell too much. This is some general things on the benefits of fire retardant composites, general attributes. What do fire retardant composites offer? Well, from a safety and hazard reduction perspective, fire retardant composites assist to reduce fire losses, related injuries and deaths by reducing the probability of serious fires developing from exposure to ignition sources of different intensities. So that sort of goes without saying. Fire retardant composites also reduce the risk of potential human health hazards in fire situations. For example, properly designed fire retardant composite materials can increase the time to rapid fire development and reduce the size of the ultimate fire, thereby increasing the time available for escape and probability of survival for occupants is a common definition of that you'll find. So flame retardant technologies, just some general stuff. I don't want to dwell on these too much before we head into more information on what we're actually doing for this collaboration. But flame retardant technologies can be broadly classified into halogenated and non-halogenated classifications or categories. Halogenated flame retardants basically contain halogens in their chemical composition, and halogens are elements in the group which include fluorine, chlorine, bromine or iodine. But as far as halogenated flame retardants go, bromine is generally, brominated compounds or polymers are generally the most effective, followed by chlorinated materials have also been used, iodine and fluorine. Those types of base compounds tend to be less effective and are not used. They are being phased out largely in a lot of applications around the world, and for various reasons which we'll go into. How do they work? They basically function in the gas phase of a fire during combustion, where they interfere with the chemistry of the flame by reacting with high energy hydrogen and hydroxy radicals. So they have a kind of a neutralizing effect and they form halide compounds. What this does is effectively stops the exothermic processes in the fire, the radical formation, which results in an overall cooling of the system, and the supply of flammable gases is also then reduced and suppressed. So if we consider the classic fire triangle, which includes the three components needed for a fire to proceed, heat, oxygen and fuel, we can say that halogenated flame retardants suppress the combustion by removing two of these components, which is thereby fuel and heat. For non-halogenated flame retardant technologies, again, it's a fairly broad overview here. There are a wide range of non-halogenated alternative flame retardants available today, and many are based on organophosphorus and nitrogen chemistries. However, other technologies also include hydrated metal compounds, and a common one is aluminum trihydrate, which has been used for many years. Not as effective. You need high loadings of ATH in general to get good reduction of flammability, but they do have very good low smoke properties, those sorts of fuel composites. But there are other issues involving reduction of mechanical strength properties and other properties which are associated with those additives. Organophosphorus flame retardants, a common example is ammonium polyphosphate. They function by promoting dehydration and carbonization at the initial decomposition of the polymer, or they react with a polymeric charring agent to create a carbonaceous char layer during the fire at the surface. Intumescent polyester and vinyl esters can be formulated and are formulated, they're possible. And in these systems, the foam char layer structure basically provides an insulation layer and a barrier to further heat transfer, volatile gases, decomposition products, and so it protects the underlying structural material from oxygen and heat. Okay, there are a number of disadvantages. There's some significant disadvantages that always have existed in using halogenated flame retardants. by comparison to non-halogenated systems. Some of these are listed here. I won't go through all of them. Major concerns are the greater potential human health hazards associated with the more toxic smoke emissions, including hazardous hydrogen bromide and similar byproducts that are formed in the gas phase during combustion of these materials. So they're highly toxic, much more than a regular set of emissions coming out of a fire, vapors. These materials also require additional synergistic compounds, other additives basically, such as antimony trioxide, generally combined with halogenated materials to achieve optimum fire retardancy. So on their own, they're not as effective. They're very effective in combination with antimony compounds. However, these other synergistic compounds, such as antimony trioxide, have associated carcinogenic properties, which is another problem. So these concerns have largely been driving the withdrawal of halogenated flame retardant materials in many areas around the world and replacement with safer non-halogenated alternatives. There are increasing regulatory constraints specifying the use of non-halogenated flame retardants, and the fire performance properties of halogenated materials will not comply with quite a few, many fire standards which have been written for many specific industry applications around the world these days. These are some of the typical advantages and disadvantages of non-halogenated alternative flame retardants, which covers a very wide range of different products. There are significantly reduced health hazards and safety hazards generally associated with the use compared to halogenated materials. So they can provide safer options with greater fire protection properties, consequently reducing the risk of loss of life in many fire situations by comparison to halogens. Some negative effects, however, on resin application, and it does depend on the additive. As I said, there's a lot of different types of technologies among non-halogenated flame retardants, but there can be, a lot of them do have negative effects on resin application properties, such as cure. Also, they can affect physical and mechanical properties, some, not all. So it's also always a challenge to balance these properties. Other resin performance properties can be more commonly encountered with the use of these materials. So they present a challenge sometimes to the resin development chemist in formulating suitable resins for fire retardant applications with these and getting around these problems by utilising other materials to overcome those sorts of deficiencies. Very common examples of well-established non-halogenated flame retardants include APP, or ammonium polyphosphate, and alumina trihydrate, as mentioned, which we've used for many years. Many different applications. Flame retardant additives, liquid versus solid form. The actual physical format is important for some applications, and in consideration of pultrusion applications, some of the advantages and disadvantages are highlighted here. Particularly if we think about pultrusion applications. For our current product development program, we've initially focused on liquid form flame retardants. They are non-halogenated class because, among other things, they provide easy handling of pultrusion line processing properties for Wagner's requirements. We don't have increases in viscosity or filtration issues as well with the filler, which can cause a number of other problems. Some of these flame retardant additives can negatively affect critical flammability, processing, handling, and performance-related properties in the cured pultruded composite. So we typically need to modify the polymer or resin formulation with other materials to offset these effects, as I've mentioned. Now, in terms of the work we're doing to develop a fire retardant version for this particular project, a fire retardant version of the resin we currently supply Wagner's, which is a fairly high performance vinyl ester called Viapal 4838. It's an epoxy bisphenol A based vinyl ester resin, has very high heat distortion temperature, good line processing properties, and we're looking to see if we can modify that to provide these properties here. Now, for this project, the set of desired flammability properties of the cured vinyl ester composite was defined by these standards according to the guys. And so these are the desired flammability ratings, if you like, to the different codes and standards that are relevant for this work. We are focusing on UL94 as far as screening properties initially in the lab, trying to achieve an approximate V0 rating. It's the highest one possible there. It's a simple self-extinguishing test, which I'll explain in a minute. The other ones, the NCC, National Construction Code Standard, was formerly the old Building Code of Australia regulations, which encompassed other standards, including AS 5030.4, which comes up in this particular one here. I won't go into that detail, just picking out one of those, BEL 40, which was mentioned by an earlier speaker here, regarding the BEL 40 standard rating. This standard relates to bushfire scenarios, as previously mentioned, and the BAL stands for bushfire attack level. BEL 40 is the second highest bushfire attack level or flammability rating under the standard. And this is typically designed or intended for specified protection of buildings from catching fire as a result of wind or airborne embers. So it sort of addresses that situation. The classification qualifies these composite materials for fire situations involving increasing levels of ember attack, burning debris by wind-borne embers, and combined with a heat flux limit of up to 40 kilowatts per metre squared, they've defined. So, and also it's to account for where there's an increased potential for exposure to flames in the application. The UL94 and ASTM D635 quite similar vertical and horizontal burn tests respectively. UL94 V0 ratings are very commonly understood throughout the fire retardant composite applications in the industry. And the UL94, if we have a look at the UL94 test, the standard itself, this is an overview of what the test is about. We can set a target of V0. The UL94, basically it specifies tests where this test specimen, it could be a laminate or a cast strip, is supported in a vertical position, a clamp, and there's flames applied to the bottom of the specimen. So the flames basically applied for 10 seconds, then removed until the flaming stops, at which time the flame is reapplied for another 10 seconds and then removed. So V0 in this table is the most difficult to achieve, and the most significant part of all of that is that you can't have any continued combustion. It's got to self-extinguish within 10 seconds after each flame application. Not always as easy as it might seem for a lot of materials, but it's a good screening test which we're applying in this case as well. Okay, so onto our laboratory program and what we're doing, and this is one area, one approach that we've taken, not the three proposed approaches. We are working on approach one at the moment with a number of different additive approaches, if you like. So in this, our resin development in this program is focusing on non-halogenated flame retardants to avoid smoke toxicity issues in particular, in attempts to meet the defined flammability properties and the regulatory and compliance requirements, but also I think if you think about future-proofing these types of materials, and for the likes of Wagner's, working on a non-halogenated system just opens up other opportunities and for a wider range of potential applications as well, not just the poles. So, our initial development work is focused on a non-halogenated flame retardant, a set of additives, and there's one particular one that we've had some success with. I'll just refer to as TSC1 here as a generic reference just for the purpose of this presentation. Flammability testing has initially been confined to UL94 vertical burn testing, and we're attempting to achieve an approximate V0 classification as mentioned as our initial round of screening. So we then will need to verify the actual UL94 ratings via an external testing, possibly at USQ. As Tristan mentioned earlier, I think that they have a UL94 test rig, which we'll need to have a look at doing some testing shortly, because we're coming to the point that we've got some suitable combinations that are worthwhile trialling and producing some composites on the line for burn testing. and further fire testing to the other standards if those results are good. Other development paths that we're also looking at, we've commenced another side part of the development. We were looking at modification of the Vipal 4838 polymer to introduce some fire retardancy, and this basically would involve chemical modification of the polymer to introduce functional groups that will basically provide fire retardant properties. So these functionalities built into the polymer, not post-added. A combination of this approach with the additive approach could be where we end up. It depends on the fire properties that we ultimately achieve in the first phase with blends. A third approach to look at modification of the 4838 with alternative eco-friendly flame retardants from USQ, in fact from the Functional Materials Group at USQ in Springfield, Pinggan. We've had some discussions there. That work has yet to commence. It involves looking at some eco-friendly flame. These are solid form flame retardants, non-halogenated, very, very interesting, but it's a third stream at the moment. We're still waiting for one of the particular materials, I think, to arrive into the country for that work. Okay, so as far as the fire retardant blends that we've been playing with on 4838, we found, I mentioned earlier, that sometimes these types of additives can affect certain properties, other properties of the resin, including the reactivity or the line curing properties. And we look at SPI reactivity tests to basic characterization to see if increasing levels of this additive, this is just a common laboratory method, actually cause any inhibition. SPI reactivity tests are common for characterizing pultrusion systems for reactivity and assessing how they'll run on the line. In this case here, these flame retardants, or this type of flame retardant, can often inhibit the curing rate of the vinyl ester and polyester resins. However, this particular material doesn't show any significant negative effects on curing at all, as can be seen in these results. And also the catalyzed pot life appears to be largely unaffected. So it's quite inert in terms of not affecting the cure, which is positive. It's a benefit in the fact that we are talking about elevated temperature curing. It's harder to achieve an inhibition effect compared to room temperature cured resin systems, but we were quite happy to see that we've got no such problems there. Similarly, for the viscosity, the effects of this additive on viscosity, it didn't show a significant effect despite this increasing viscosity with the additive level. Those viscosities are well within the acceptable ranges for good or satisfactory protrusion line processing with the resin. So you don't see any problems there with the actual increase in viscosity, which was not regarded as significant across those levels. Okay, so as far as the UL94 flammability, some results here. We found that from our initial UL94 fire testing evaluations within Allnex, and we don't have a fully controlled conditions on our reg, we found approximate UL94 V0 results can be achieved at levels of this additive between 10 and 15%, being around about 12%, we believe is the sweet spot for that one there. It was quite positive. The effect on fire retardancy was quite definite. Problem is, as I mentioned before, another issue is that these types of materials can sometimes plasticize the cured matrix. So at the addition rates we're looking at with this particular non-halogenated flame retardant, we did see quite a significant reduction, which was not unexpected to us, looking at what the material is from our past experience with similar types of flame retardant materials. This liquid flame retardant did drop the HTT as we increased the level, as you can see there, which is a bit of a problem. So heat deflection temperature is a fairly critical property in terms of things like heat resistance. So we needed to look at other ways of altering that. And one way was to look at synergistic, other additives or other flame retardants in combination with the initial TFC additive. Initial synergistic, we tried another synergist that was suggested, industry recommended synergist. It didn't work. We've tried a few options. However, one particular reactive non-halogenated flame retardant, which we'll call HP1 here, did actually allow us to reduce the TFC level in the formulation. This new flame retardant, it's also a liquid form, so we've maintained those good processing properties potentially for the lime, for the resin in a pultrusion process. But where this one differs from the TF1 is that it's a reactive material. It means it actually reacts and cross-links into the final cured resin structure, so you don't have an effect on HDT. So we basically could reduce the TFC level in the formulation by using this other material in combination. So we sort of got a synergistic effect, and we can achieve the same low flammability, the low UL94 flammability results by using a lower amount of the TFC. So with the aim being to maximize the HDT properties. We'll get them back up again. On the reactivity side, we didn't actually see any issues there. No significant effects that it had on the material at all. The increase in gel time is not regarded as significant, so curing under the elevated temperature curing conditions were comparable. And I mentioned Duracade 640-900 is another resin that it shows much wider range or much longer SPI gel times, and that still works quite well on the Wagner's line. So we know for a fact that these SPI reactivity values are still virtually unaffected by our experience. Heat distortion temperature, as I mentioned, by incorporating a combination of the two flame retardants, we managed to reduce that plasticizing effect by reducing the amount of TFC, and we brought that HDT back up to a reasonable, about 116 and a half on this test here. The Viapal 4838, this was another test, 130, 135 is typically, each time you do a test, you do another run, obviously, as another control. But it's a lot better than 83 or the maximum we could get down on the from the previous test without the modification with the new reactive flame retardant. So we're quite pleased with that one. Okay, so further work that we have, we need to optimize the ratio and formulation levels of these two flame retardants for this particular part, just to maximize the UL94 fire retardancy properties, and maintain the maximum HDT. I believe that's been done. So we're really at the stage now that we want to prepare some small trial batch and even some lab batch samples, which I believe that the guys can run on at USQ, possibly at Wagner's as well, in a smaller scale trial. And that the main reason there, to have a look at the line processing and curing properties. The guys can obviously have a look at this through their DEA analysis tools as well, to compare how this would compare against the current non-fire retardant version of the resin. But we also need to produce some test laminates and pultruded representative laminates for outside fire testing as well. There'll be external UL94 fire testing, and there are a few options here as well, of course, as USQ's rig as well, which we obviously initially want to do some internal testing on that. Depending on those properties, and we can confirm a V0 verification is required, then we can look at further outside flammability testing for BAL 40, the NCC, and the ASTM D635 requirement. That's a fairly easy self-extinguished test to pass. So mainly the BAL 40 and the NCC will be interested to see how we go there once we've optimized the formulation. And as mentioned, that the next part, which which we're just getting underway, has taken a while. We've sourced 2 compounds potentially that could potentially be used to modify the 4838 polymer to introduce some fire retardant chemical functionalities into the backbone. It's early days on that, but we have just made a start on that recently. Okay, that was it for me. If there's any questions?
Thanks, Dean, for your presentation. Anyone have a question for Dean? Any question for Dean? I will post Dean contact email in the chat. So anyone would like to ask Dean on their product and the fire retardant is welcome to shoot an email through to Dean. Thanks, Dean, for that.
No problem, Omar. Thank you very much.
Thank you so much. Actually, I would like at the end of this webinar, I would like actually to thank our hard workers and post-grads actually who are working on this project for their hard work, and for our collaborators and industrial partners. I would like also to thank Schweissensing for preparing this webinar and initiating this meeting. Thank you all for your attendance and your patience as well. And hopefully we gave you actually informative knowledge on this project, and we are happy to receive your comments and suggestions and questions also on our contact. Thank you all. Now we are closing the meeting. See you soon and be safe.
Thank you, Omar.
Thanks, Dean.